Hello everyone. Today we're going to start with subspaces. The first thing we're going to do is we're going to talk about the definition. Now earlier we learned about vector spaces. Suppose I have a vector space, this suppose is my V, and I take a small set of it. Okay, so let be this little set H here. And this H is a subset of V. Okay. We like to know whether it also has the same qualities and properties as the vector space. And if it is, then we call this a subspace. So we'd like to know what are those properties which will make this H a subspace of V. So let's look at the definition now. We say a set H is a subspace of a vector space V if the following holds. First thing is, H is a subset of V. Sorry guys, that's a typo. Now, the second property is needed is that the zero vector of the bigger set, that is V for us, is in H. In other words, in simple words, you can say zero. The zero vector is denoted by this big zero here, belongs to H. And this zero has to come from this capital V. H is closed under vector addition. That means if I take two vectors, U and V in H, important, they're coming from the elements of this little blue. That means if I add these two elements, U and V, they also belong to H. This is called the closure property. The last property which is needed is H is closed under multiplication by scalars. What simply means is if a U is a vector in H and I have a C, a scalar, then C times U should also belong to H. This is called the scalar multiplication closure property. So if I have a subset of a vector space and all these four properties are satisfied by the subset, then that subset becomes a subspace. Okay, much more easy to prove a subspace than a vector space. You can see that. Only four properties were done as compared to vector space that you had 10 properties. Okay, let's look at some observations of subspace. So the observations that every subspace is a vector space. In other words, if we are proving that this is a vector, the subset is a subspace, then all these four properties can be used in proving all the 10 axioms of the vector space. It's much more easy to have a subspace than the vector space, as I said. So every subspace is a vector space. Conversely, every vector space is a subspace of itself and possibly of other large spaces. So this is important. So if I prove that something is a subspace by using those four properties, I can automatically say it is a vector space. Or if I know it is a vector space, then because every vector space is a subspace. The reason is this: let V be a vector space. Okay? If V is a vector space, V is a subset of V. Right? Then zero element belongs to V. If I take two elements U and V, then U plus V belongs to V because V is a vector space. And if I have a alpha, which is a scalar, alpha times U belongs to V. So clearly all the four properties are already defined. So V is a subspace. So every vector space is a subspace and every subspace is a vector space. Let's now look at some concrete examples. Okay, the first one. Let's look at the set D22. D22 is a set of all diagonals, which is given in the form D10, 0, D2, when D1, D2 are real numbers. It's a set of all diagonals of matrix of size 2 by 2. We are defining this D22 by the vector addition and scalar multiplication as shown here. So if I have two vectors in D22, So what is this vector A? My vector A is A1, 0, 0, A2. My vector B is vector B1, 0, 0, B2. Okay, so I have two matrices, A and B in D2. So when I add them, I'm basically adding the corresponding elements. So A1 plus B1, 0, 0, A2 plus B2. If I have an element A and I multiply it by a scalar alpha, then alpha times A, alpha A1, 0, 0, alpha A2 is defined in this form. So the question is, prove that D22 is a subspace of M22. Now remember, if you have to prove that something is a subspace, we need to prove all the four properties. And let's look at what is M22. Remember the familiar vector space of M22, the set of all matrices of size 2 by 2? That's the M22 I'm talking about. Okay, so let's first prove that D22 is a subspace of M22. Okay, now remember M22 is a collection of all matrices of size 2 by 2, and we know it is a vector space, which is defined by the usual matrix addition and scalar multiplication. You can go back and check into your notes. It is defined what the addition and scalar multiplication is. But the question over here is D22 is a subspace. We have to prove that of M22. Now, the first thing is, you have to prove that D22 is a subset of M22. Now, clearly, by the definition of D22, D22 is a subset. Remember what D22 looks like. D22 is this. This is my D22. It's a collection of 2 by 2 where the elements on the diagonal starting from top left to bottom right is having D1 and D2, but the rest of the elements are zeros. So clearly it looks like a M22. It's just a matrix of size 2 by 2. So clearly the first thing is proved. Second, the zero vector. Now, if I take my zero vector, if this is 0, 0, 0, where, we are assuming D1 is 0 and D2 is 0. Remember, D1 and D2 are 0. Clearly, it belongs to D22 because the other elements, they're already defined. This D1 is 0, D2 is 0. So clearly, 0 belongs to D22. Third, we say, let, say, matrix A and B belong to D22. What is it? So it's A1 plus B1. That's how it is defined. 0 is A2 plus B2. Clearly, we notice that A1 and B1 and A2 and B2, the thing is, we have to look at it as, does it look like a D22 element? Yes, because this is 0 and this is 0. Remember, I've already said how an A and B looks like in the previous section. Here's my A and B. So when I add these two vectors, it perfectly looks like a vector element of D22 because the elements, it has two zero elements, one which is 0 in the first or second column, and the second is a 0 in the second row from the first column. That's where these are 0, and that's exactly an element of D22. Okay, so if I take an element, the fourth part, if alpha is a scalar, and the way we are defined, so alpha times A is what? Alpha A1, 0, 0, alpha A2. That is basically the way the definition is given. It automatically makes a closure under scalar multiplication. So D22. So all the four properties are satisfied, and hence D22 is a subspace. Okay, so that's an example. Let's look at trivial subspaces. If V is a vector space, the set which consists of only the zero vector, that's the one I'm saying here. I have a vector which consists of the zero vector. It is always a subspace of V. We call it the zero subspace and we write it as this. And we also proved that V is also a subspace of itself. So there are two subspaces, the zero subspace and the original vector space V. These are called trivial subspaces. And one more important thing, that a zero subspace is a subspace of every vector space. Now we are going to go back to something we learned long time ago, which was the spanning sets. Now, remember, what is a spanning set? Spanning set is nothing but all possible linear combinations of the vectors which are in the set. For example, if I have a vector, say v1 to vp, and I look at all, so I have a set of vectors from v1 to vp, and I look at all possible linear combinations of v1 to vp, then that is called a spanning set. It is the set of all linear combinations of v1 to vp. Now, if you're forgetting what is meaning by linear combination, it is the sum of scalar multiples of the vectors. For example, you can think of this one as alpha v1 plus alpha 1 v1, alpha 2 v2, alpha p vp. Now these alpha i's are, constants or real numbers. Okay, so that's what basically it is, a set of all linear combinations of the vectors v1 to vp. Now this spanning set has a very, very important role to play in vector spaces. Let's see how that role comes about. I'm going to start with a very simple one. If I have two vectors in a vector space, capital V, then I look at all possible linear combinations of v1 and v2. And that means it becomes a spanning set. And I say, hey, let me write that as an H. So I would like to prove that this H is a subspace of V. Okay? So what we're saying is, if I have a vector space and I pick only two elements, say only two, just to start with, and I look at all possible linear combinations and I put them in a set called H, and we denote it by span of v1 to v2, we are going to show that this spanning set is always a subspace of V. So the first thing is, it is H a subset of V. That's what we start with. If it is a subset, very good. Okay, so to say that, now first thing, by the virtue of definition of H, H is a subset of V. This is a subset, guys. Symbol for subset. Okay? Now, so we don't have to say, because of the definition. What is the definition? If you forget it, guys, keep this in mind. This is alpha times V1 plus beta times V2. And alpha and beta are scalars, or real numbers, or whatever you want to call them. Now notice, what is V? V, remember all those 10 axioms? And you see it's a scalar multiplication, and then you add it to another scalar multiplication. It is still an element of V. Okay, second, the Z, if I take a 0, I can write 0 as 0 times v1 plus 0 times v2. Because that's what you do. It's a spanning set. All possible linear combinations. Clearly, I have a linear combination of the vector v1 and v2. Clearly, it belongs to H. Okay. This, guys, remember, belongs to or is an element of, if you forget. Let's look at third. If I have two elements, okay, I'm going to change the variables. Let's say M is an element, alpha v1 plus beta v2, and I have an element N. Let's say this is alpha and beta, gamma and delta. Gamma v1 plus delta v2 belongs to H. We have to prove that M plus N is also in H. So let's just do that. Alpha v1 plus beta v2 plus gamma v1 plus delta v2, which is, again, not a simple addition. So, v1 and v1 I can add together. So alpha plus gamma v1 plus beta plus delta v2. Clearly, I see a linear combination. It belongs to H. So that means the vector addition is closed under the subset H. Then the last thing, we have to prove, let alpha be a scalar. Oh no, we already used an alpha. What do you want? Do you want a smiley face? Let's do a smiley face. Haven't done it for a pretty long time. So this smiley face be a scalar. Okay. Then a smiley face times v1 is going to be what? A smiley face times a vector, sorry. Let's look at the smiley face is an M, sorry, I made a mistake here, guys. Yeah, a smiley face and M. M is in vector, okay, here. So we can say here M is a vector in H. So smiley face times M is smiley face times alpha v1 plus smiley face times beta v2. Okay. Now clearly, again I see a linear combination. Do you see that over here? So I can combine that and I can write this. Let's just take a nicer more. So what is this? So I can write this as smiley face alpha 1 v1 plus smiley face beta v2. Oh, sorry, alpha, not this. Which can be written as, so clearly, which implies that my smiley face and M, okay, my smiley face kind of literally bumped up. Okay, so my smiley face and M belongs to H. Guys, you just need some scalars and that's it. So anything can become a scalar. My smiley face is scalar, okay? Yeah, we haven't done it for a pretty long time. You can see that. Okay, so we have proved all the 4 properties which are needed for a subspace. And what do we notice? Let's have the green thing then, that this H, a spanning set, that H, which is the span of 2 vectors v and v2, is a subspace. Now, the most important thing for us is that any spanning set of a vector space will always be a subspace, and that's what we're going to literally be using in proving some of the questions. So let's talk about a theorem. Now, this was only for 2 vectors. Okay, we can generalize this theorem. This is called the spanning set is a subspace. So if I had said p vectors, v1, v2, vp, in a vector space capital V, then the spanning of v1, v2, vp is a subspace of V. What basically this saying is that all possible linear combinations of some vectors in a vector space will become a subspace. So the spanning set, guys, anytime you can see a spanning set of vectors of a vector space, automatically in your mind, it is a subspace, and that's literally what we'll be using in proving some of the questions later. Okay, now let's look at, so the proof is very similar to the above example. That is not the one I'm more concerned, I'm very focusing on. My focus is apply this theorem that spanning set is a subspace. Okay, now there are certain terminologies that the spanning set is also called the subspace spanned by the vectors v1 to vp, or we can say the subspace generated by the v1 to vp. And if I've given any subspace H of V, a spanning set for H is a set of vectors in P such that H equals the span. That's a different ways of looking at the same thing. So our main important part is, if I see a set of vectors and I look at the spanning set of the vectors which are coming from that vector space, in my mind, it is a subspace. Okay, now we're going to do some examples. Now let H be the set of all vectors of the form 2t, 0t. We are going to show that this H is a subspace of R3. Now remember, what did we just say? That if you have any set which can be represented as a spanning set, then by default the spanning set is a subspace. So our H is the set of the vectors of this form. Okay? So let's look at the vectors. So how do we write this vector? 2t, 0t. I can write this as 2, not 2, but t out, because t is the common factor. If I take the t out, what do I see? 2 or 1. So what is H? It is a set of all the vectors of this form, where t is any element. T is a scalar or a real number, you can say that. So what is this? You see H, so what is my H? My H from here is the span of which vector? Is the span of the vector 2 or 1. And what we just proved, that if you have a spanning set, and we know R3 is a vector space also. R3, we know from the very beginning of this chapter, is a vector space. Okay? And clearly 2 or 1 is an element of R3. And what did we just say? That this set, which is of this form 2t, 0t, is nothing but the spanning of all possible combinations of 2 or 1. And then by the spanning set theorem, which we just learned, H is a subspace of R3. So notice, in order to prove something is a subspace of a given vector space, we don't have to go through all those 4 properties. Just apply that theorem, the spanning set subspace theorem. Yeah, that's the spanning set. Do you see that here? The spanning set is a subspace. So that is what important part for us, the spanning set subspace. Okay, let's look at another example. Let W be the set of all the vectors of the form s plus 3t, s minus t, 2s minus t, and 4t. We want to show that this W is a subspace of R4. Okay, so if I can write W as a spanning set of some vectors, then by the spanning set we just proved that every spanning set is a subspace, then we are done. So let's look at the vectors here. Okay, and also remember R4, guys, is a vector space. Okay, let's look at this one. S plus 3t, s minus t, 2s minus t, 4t. Now I can write this as all the s's together, s, 2s, 0, plus t, 3t minus t minus t 4t. Okay, now s can be taken common from here. 1, 1, 2, 0. And I can take the t common out from the second vector here. 3 minus 1, 4. Notice the w, which is set of all those forms, is nothing but linear combination of the vector 1, 1, 2, 0 and 3 minus 1, 4. So w is nothing but the span of the vectors 1, 1, 2, 0 and commas, doesn't look like a comma, okay, comma, 3 minus 1, 4. And we just said that a spanning set of vectors is a subspace. We know that the spanning set is a subspace. Hence, W is a subspace of R4. Very important, guys, because the elements of W are elements of R4. That's very, very important. Keep that in mind. These are elements which have 4 rows. You know, 1, 1, 2, 0. So it's an element of R4. Only then you have to, whenever you're looking at a spanning set and you're proving it as a subspace of another vector space, you have to make sure the elements are matching. Because R4 will have the elements or vectors which will have 4 rows in them. So W has 4 elements of which have 4 rows. So the elements are actually elements of R4. That's very important. If you're saying something is subspace, so that the way the elements are consisting of those sets, they have to match the bigger set. Okay, now we have learned about looking at different sets, and we say, oh yes, it is a subspace. So let's look at an example where it is not a subspace. And guys, I'm taking all these examples from the book. Okay, here, given W, the set of all the vectors of the form minus A plus 1, A minus 6B, 2B plus A, show that W is not a subspace of R3. Okay, it is not. In other words, if I'm not able to write it as a form, so clearly if I can't write it as a form of, say, what we would say, a spanning set or something, or we can pick up some elements to show that it is not a subspace. Okay, so the first thing is, how do you know it is not a subspace? The first thing is, even if I take the A's and the B's out, this is going to be a problem to me. Okay, I'm going to show you literally why it is not a subspace. First, I'm going to prove it, and then I'm going to show you also when I create those little, whether it can be written as a spanning set. So here's, if it is not a subspace, remember, not means one example is needed to prove that it is not a subspace. So here, because these are vectors and A and B can be any real numbers, you say let A and B, A is 0 and B is 0. Okay, so we're going to say A equal to B. So what do we get? So one element, if A is 0, B is 0, is going to be what? 1, 0, 0. Do you see that? In other words, for it to be a subspace, remember the 4 properties have to be proved, that it has to be a subspace. That means it should have the 0 vector. Even if I put A's and B's to be 0, I will never get a 0 vector. Do you see that here? So 0 vector, the 0, the 0, 0 does not belong to W. And it is one of the most important part that if it is a subspace, the 0 vector has to belong to that subspace. 0 does not belong to W. Thus, W is not a subspace of R3. Okay? As I said, I'm going to show you, just for practice sake, we have already proved the answer. Why is it not a subspace? Only we need one example to show that out of the 4 axioms, one of them is not present. And most of the time when you're proving something not a subspace, always look for the 0 vector. That's the hint I give you. Okay, now I'm going to show you something here is how I can do some little algebra on it and see how I can write, them as a set of some, can it write it as a spanning set or not? You will notice this cannot be written as a spanning set also. Just to show you, it's a practice, guys, okay? Even though we are done with the answer, guys, this is the answer. And now just extra work to show you here. Okay, so I'm going to show you on the other side here. So I'm going to use a blue. So how do we write this as, if I want to split and write it as, is it possible to write it as a spanning set of some vectors? That's my thing. Can I write it as a spanning set of some vectors? And you will notice not. So the first thing is I can write all the A's together, minus A, then all the B's together, 0 minus 6B, a 2B, but I'm missing a 1, that's plus 1, 0, 0. So this is A, minus 1, 1, 1, take the B out, 0 minus 6, 2, plus 1, 0, 0. Notice, I cannot write this set of vectors as a spanning set of vectors. Because spanning set means I will have to have, so this one is the constant which is always multiplied. Do you see that over here? Okay. But here's the key. If I have to prove not a subspace, very important, if it is not a subspace, one example is needed and it's more than enough. Okay, now, here are the set of questions I want you to practice from the book. Number 9, 11, 13, 15, 17, 21, and 22. Thank you.